Hello and welcome to NASA's Break the Ice Lunar Challenge second webinar. Today we're going to be focused on discussing lunar icy regolith and controlled low strength materials. There will be a Q&A session at the end of this webinar, but with that, let's get into it. So just to do some quick housekeeping, we will have 3 speakers today. Please enter your questions into the Q&A tab, and we will be processing questions and answering them live at the end of this webinar. With that, I will pass it over to Kevin Cannon. Take it away, Kevin.
Great, thank you. So my name is Kevin Cannon. I'm an assistant professor at Colorado School of Mines in the geology department and also our space resources program. And today I'm going to talk about kind of the scientific backgrounds of lunar ice, what the evidence is that ice exists, and what it might be like on the surface. So next slide. Okay, so first I just want to start with why we think there might be ice or why there could be ice at the poles of the moon. The first reason is that the moon doesn't have an atmosphere, and so there's no way to transfer heat. And what that means is that the temperature at a given location entirely depends on how much sunlight that location receives. And then secondly, because the moon has a very small tilt, it's only tilted about 1 degree, whereas the Earth is tilted about 23.5 degrees. What that means is that if you're at the poles of the moon, the sunlight is always coming in at a very low glancing angle. So when you combine that with the kind of rough topography, all the craters at the poles, you end up with some regions that never actually receive direct sunlight, and those are the permanently shadowed regions, or PSRs. And within those are some of the coldest areas on the moon, in fact, the coldest areas in the solar system. These are the cold traps, which are actually cold enough to hold on to water in solid form in a vacuum on a billion-year time scale. Okay, and so going back to the 1950s and 1960s, people started to predict that these areas at the poles of the moon could actually trap water and could have deposits of water ice. Next slide. Okay, so there were some hints, some clues in the late 90s, early 2000s that there might in fact actually be water ice present at the poles. But what I'd say is probably the most direct detection came in 2009 with NASA's LCROSS mission. And in this mission, what they did is they purposefully crashed the upper stage of a rocket into one of the coldest areas at the south pole of the moon in Cabeus crater. And then they had a bunch of instruments that looked at the plume of material that came up when that rocket stage impacted the surface. And so they were able to detect water ice, maybe somewhere on the order of 5 weight%, and also some other volatile species as well, some sulfur, some nitrogen, some carbon-bearing ices. Now, recently, people have gone back and re-looked at this data and have kind of tried to interpret where that ice actually was in the ground. And based on that, there's a suggestion that perhaps the ice content increases with depth, and there may be a fairly high strength layer about 5 or 6 meters below the surface. It's possible that that could be an ice cemented layer. Next slide. Okay, there have also subsequent to that been detections of ice directly at the surface. So this is using reflectance spectroscopy, looking at the sunlight that's reflected off and looking for kind of fingerprints in those spectra of ice molecules. And so using different instruments, kind of patchy ice occurrences have been detected, but it's very difficult to tell if this is just a kind of transient frost that's on the surface or if it's actually a deeper ice deposit. Next slide. Okay, and then we've actually been able to see into these permanently shadowed regions, into these PSRs, because even though they don't get direct sunlight, they do get some indirect sunlight that bounces into them. And so recently people have developed some machine learning techniques to enhance these images that we have of these shadowed regions. You can see an example here. So when we look into one of these PSRs, we don't actually see any evidence for ice. There's no big chunks of ice, there's no ice sheets. So when we're talking about ice at the poles of the moon, we're really not talking about, kind of skating rinks at the surface that you might see on Mars or Mercury. It seems that if there is a lot of ice, it's probably buried at depth, and the ice could be in different forms. We don't quite know what the texture of that ice is. Next slide. Okay, and then this is just to emphasize that all the techniques that we might use to try and detect or infer ice, a lot of those are remote sensing techniques that are carried out from orbit, so from orbiting satellites using different parts of the EM spectrum. And what we have to keep in mind is that each of those techniques, whether it be reflectance spectroscopy or neutron spectroscopy or radar, they all have a different depth that they penetrate to beneath the surface. So some of those techniques that I mentioned before on the maps that I showed, you're really only seeing microns beneath the surface, whereas some things like radar or the L-cross impact could penetrate meters beneath the surface. So we kind of have to distinguish between ice that's right at the surface, right at the optical surface, shallow ice within the upper meter, and then deeper ice that could be more than a meter down. Next slide. Okay, and so scientifically, we kind of have to think of this as an integrated system in terms of, how did the ice get there in the first place? What were the sources of that water? So we think that a lot of that water was probably brought by asteroids and comets that collided with the moon. There could also be water in volcanic gases that are output during the early volcanically active phases of the moon's history. So that puts water into the system. And then once that water is there, it can move around the moon via a couple of different mechanisms. So one is that individual molecules of water could actually hop across the surface and eventually reach the poles. The other one that's maybe more in favor these days is that if you have a large enough amount of water injected into the moon system from a large impact, you could actually form a thin atmosphere that lasts for a few thousand years, and water vapor could be transported in that atmosphere and deposited at the poles. So once that water is actually deposited at the surface of these cold traps, there are a variety of different processes that act on it. We have impacts, smaller impacts hitting the surface of the moon all the time. Those are kind of churning up the soil. We have larger impacts nearby that could bury those deposits of ice. And then we have changing thermal conditions. So the moon might be changing its orientation. That could be warming up certain areas and creating cold traps in new areas. So kind of have to consider all these different processes in the evolution of these ice deposits over time. Next slide. Okay, and there are some predictions quite recently that some of these layers of ice, at least initially when they were laid down, could be quite thick. So we could actually be talking about meters thick layers of ice, or maybe even tens or hundreds of meters originally. But that was probably a long time ago, billions of years ago, when we had larger events to deposit more water. And it's not clear if we had that much ice at the surface originally, what's happened to it and how much of it has survived. Next slide. Okay, so I mentioned before that we really don't know what the texture of the ice is at the poles because we haven't gone down there to actually pick up samples and see what they look like. So on the left here, this is a graphic that we've created that's meant to show some different possibilities of what we could have. So in theory, we could have discrete grains of ice that are kind of mixed into the soil. Those could be coarse grains, they could be really fine. We could have a coating of ice or a rind on these grains of regolith. And these grains that we're talking about, the regolith is typically tens of microns in size. We could have regolith that's kind of stuck together with ice, so it could be filling the pore space and creating kind of a stronger, more competent layer. And then we could have some more exotic forms on the bottom there that are created during impact processing. So all of these textures probably do exist to some extent. We could think about the processes that form them, but we don't really know which ones are dominant and how much ice there is and where it kind of is at depth within the regolith column. Next slide. Okay, so our first chance to get what we call ground truth, so kind of validation of all these orbital remote sensing, is something called the Viper mission. So this is being run by NASA. It's been delayed recently, so it'll now be launching in late 2024. And this is actually the first kind of ground-based rover mission to investigate these possible ice deposits at the poles of the moon, specifically the South Pole. And Viper is outfitted with 4 different instruments. These can be thought of as scientific instruments with some applicability to ice as a resource. So it has a neutron spectrometer. That's an instrument that can infer the presence of ice up to a meter beneath the surface. It has a drill made by Honeybee Robotics that's going to sample from up to a meter deep. And then it has two instruments, a mass spectrometer and a visible imaging spectrometer, that are basically going to look at those chunks of material that are excavated by the drill and try and see if there is water ice and other volatiles. So based on these instruments, we might get some idea of those textures and some idea of the amount of ice that's present, at least in the upper meter. Okay, next slide. So if we really wanted to look at ice as a resource, we might want to go to some of these larger craters. I mentioned Cabeus crater. That's one of the coldest areas where the Alcross impact happened. There are some giant craters that host cold traps at the south pole of the moon, like Hayworth and Shoemaker and Faustini. The problem is that it's fairly difficult to get access into those craters. So this is some work here showing the accessibility if you wanted to land in a well-lit area and then go down into one of these cold traps. Some of these distances are tens of kilometers and involve going down steep slopes. And unfortunately, the Viper rover just isn't capable of getting into some of these larger areas. It's a solar-powered rover, so it has to recharge in the sunlight. And so next slide. So the Viper rover is going to be sent instead to an area that has these smaller cold traps, these smaller permanently shadowed regions. And it's going to kind of, dash in and then dash out into these shallow deposits. So this will give us some sense of, in maybe the worst case scenario, is there a lot of ice and what it's like? But ultimately, hopefully we develop the capabilities to go into some of these larger areas with these giant potential ice fields that might be buried at depth. So hopefully that just gives you a little bit of a primer on, why we think there's ice at the poles of the moon. Some of the detections that have been made, indirect and direct, and some of the open questions that still remain about the strength of the ice and the texture and the form it's actually in. So the Break the Ice challenge is making some assumptions, some reasonable assumptions about what those ice deposits might be like, and that's the basis for the simulated material that is going to be talked about next. Thank you.
Great, thank you very much, Kevin. And with that, I will pass it over to Pete. Pete, take it away.
Thank you, Kevin and Oliver. So I'm Pete Corrado. I'm part of the challenge team that helped develop the rules for Break the Ice Lunar Challenge. And simulating Icy Regolith was one of the more difficult parts of developing the rules. Next slide, please, Ollie. So it's a challenge to create a challenge. The challenge for us is you only get to do this once. It's not like developing a test in thermodynamics where by the third time you deliver the course, you know exactly how to create the test. We'll only have this challenge once ever, and there were no previous challenges that we could lean on for lessons learned. So it's a one-time event, and I hope all the folks who intend to enter understand that we work very hard on developing these rules. One of the most difficult parts of it is simulating the Icy Regolith. So as Kevin pointed out, we really don't know what we're simulating. And therefore, the rules as written are quite nebulous, and thus it actually has created the most common source of inquiries from teams to the folks running the challenge. So I hope the teams understand there's little we can offer you in answer to like very specific questions. Like if you had a question like, well, what would NASA recommend to be the best type of fine aggregate in my CLSM? Well, we can't recommend anything because we don't know. We're expecting you to make a decision and provide background on how you made that decision. So please keep that in mind as we go through the rest of the webinar here. The very specific questions, how much water would I put in my mixture? We're not going to be able to answer because we don't know the answer, and it's going to be specific to what you intend to use in your entry. So next slide, Ollie. So even though we don't know what we're trying to simulate, we do have some top level requirements that we have to address. So NASA's technical specialists, the principal technologists, I've identified a number of technology gaps that this challenge is intending to try and close. Some of those gaps are very specific to the simulated regolith. So we're supposed to deliver large quantities. Of course, if you talk to a terrestrial miner, the quantities we're delivering are really minor, but in terms of lunar exploration as it exists right now, these are large quantities of material to move around. We have to demonstrate both excavation and transportation. So all three of these will be impacted by the properties of the regolith we simulate. The other required attribute is we need to try and simulate lunar conditions, which is really hard considering we're doing this whole challenge on the surface of the Earth. Next slide, Ollie. So Kevin had a great slide, which I intend to steal and use in future presentations, that shows a variety of geological formations of the combination of the rocky part of the regolith and granular ice, whether it's fused to the surface of the rocky grains, is an actual ice grain that's intermixed with the rocky grains, or some type of cementitious action of water cementing rocky grains together. So that's one of the properties that's a challenge for us to come up with a simulation method. And down the bottom right here, you can see that people on Earth have gone into the labs and tried a variety of ways of creating icy regolith. And the one thing that's agreed to is the water content has a big impact on the strength of the material. So this just shows compressive strength versus water content. You can see even small percentage weights of water can produce massive jumps in compressive strength. So given that as background, let's go to the next slide, Ollie. What do we need to simulate to close the technology gaps we're given and deal with an unknown material? So there are lots of properties for icy regolith that are important, like water content, like purity of the water. So if you intend to electrolyze it or drink it, that's a real important property. Not very important for our challenge of excavating and delivering. So it's primarily the mechanical properties we're interested in. And there's a variety of mechanical properties to geological deposits. So particle size distribution. Am I dealing with sand grains? Am I dealing with gravel? Am I dealing with something bigger than gravel sizes? Strength is obvious. What about the density? Okay, so since we're on Earth, the density is going to be regular Earth gravity density, but it could, of course, affect how you design your robotic system to deliver. Abrasion's a big one. We're not even going to try and get into how aggressive the grain particles are, the dusty grains on the moon, and how it affects the equipment that's going to do the excavation and transportation. Void ratios, just many, many more mechanical properties of regolith deposits. So to try and make this a challenge that's doable, we focused in on one, and that's just strength. So we're talking about unconfined compressive strength. So can we go to the next slide? So we have a wide range of strengths we can address given the unknowns here, specifically how the water ice intermingles with the rocky grains. So if the water ice is a bunch of really robust ice particles, and it's just the mixture of ice particles and rock particles, you're pretty much trying to dig sand. On the Earth, we do have experience with permanently frozen deposits called permafrost. So excavating permafrost, there's huge amounts of literature on this. And the methods are quite simple. You either need very heavy equipment like it's shown here, or you need explosives, or you have to go in and melt it. So here's an example from a permafrost excavation expert company. And you can see that once this breaker is done, got some very large pieces of material to move here. So the answer is probably somewhere in between the two, the mixture of grains and really super hard permafrost. So this is like excavating real concrete, like the concrete in a driveway. Let's go to the next slide, Holly. So now the challenge team is forced to find realistic constraints because we want to make this something that people can participate in and have a positive experience. So we needed something that was affordable. Okay, we're not going to ask people to go out and buy or suggest. We're not asking you to do anything. It's up to you to come up with your mixture design. But you don't need to go, well, I got to go buy some lunar simulant. It should be an achievable simulation. So we're not down at really low temperatures here. It's got to be available. Can't be made of that material that I know in my professional life as unobtainium. So it's got to be something that most people could lay their hands on. We need something reliable. We need a simulant that is not brand new, that there's a long history of technology associated with what we're recommending. And we'd like it to be repeatable, not just within a single team where you're trying over and over again to dial in your perfect mixture, but we want parity of the materials across all the teams in many geological locations. So when you're creating a concrete mixture, it's very much a function of where you live. Am I up in Vermont where there's lots of great granite? Am I down in South Florida where I have a really soft limestone? You can make concrete in both regions, but it takes some effort. And so we need testing methods that allow us to compare teams from one area to the other. Next slide, Holly. So what we've chosen, and there's actually some researchers out there who recommend this as a way to simulate Icy Regolith, is something that goes by the term consolidated low strength material, or CLSM. So this material's been around for a long time, and it had a lot of other names before it became more mainstream, like fillcrete or flowable fill. And where it was developed was in the construction industry. When you had a large excavation and you needed to backfill it, you could backfill with granular soils, which takes a lot of labor to place properly. You have to place them in layers of, say, 6 to 12 inches, and then go in, usually in an area like this, maybe with hand tools to tamp the material down, and then place another layer. And although you're just using dirt, you're using a lot of expensive labor to do that. So it was developed to use just really low strength concrete, which basically you pour in to fill it up. And it became like a pretty robust soil deposit. So this is the material we've selected to do the simulations with. Let's go to the next slide, Ollie. So CLSM, and we've given you the ACI report, which provides a lot of good background information on this material. And we've only defined one physical attribute, and that's the unconfined compressive strength. That's what every team needs to meet, no matter where you are geologically around the country. So we want the strength of the material to be challenging. So at 1.5 MPa, you'll see in Dr. Munchie's presentation coming up, he's at the high end of what's called excavatable CLSM. So it's going to be rugged to extract. It's not going to be something you would necessarily go out with a shovel and be able to dig up, but it's still relatively soft. So the other constraint we have is on material choices. So CLSM is typically made of cementitious material, whether it's Portland cement, fly ash, and aggregate, which is can be sand. If you wanted to use lunar simulant, you could use that. You could put a little bit of pea gravel in there, a variety of things. But we're not going to allow the use of lightweight aggregate, which would be something like perlite or expanded shale. The reason for that is that's probably going to be a little easier to excavate than if you used what's normally called normal weight aggregate. Down at the bottom, it shows a picture of strength gain versus time. So all concrete mixtures go through a chemical reaction and they gain strength over time as the reaction goes forward. So you're going to have to do some trial mixes of your CLSM to see how it gains strength so that you'll predict when you're going to start your test. So you can't start testing until you've tested some of your mixture and shown it to have a unconfined compressive strength of at least 1.5 MPa. As soon as you perform that test and you're at 1.5 or above, you can begin your excavation. The image here is to show you that you probably want to spend some time playing with this mixture to make sure it doesn't have an aggressive strength gain with time. So mixture 1 would probably be a good mixture to test with because it hits that 1.5 MPa number and then does not gain significant strength over the 15 days you're testing. And there will be strength gain during the test. Whereas if you had a mixture like mixture 2, by the end of 15 days, you're really excavating some pretty hard material. So the design of this mixture will be important to your performance in the challenge. Next, Holly. Right. The other part of our simulation here is we're trying to simulate a large icy regolith deposit, something that would be commercially developable by a mining corporation. So they're not going to go in to just dig out a small pit of icy regolith. They want something they'll be able to work on for years. So that's why we've created the geometry shown in the rules, where we have a certain depth of deposit, and then we have this buffer area around it. So we've already had a couple of questions on the buffer. We place the buffer at the same time of the material to be excavated. What happens if we dig into the buffer? So the buffer is there to kind of simulate that this deposit goes on. And we want to stay within an area where we're not necessarily totally fracturing the simulated regolith we've put in. So that's the purpose of the buffer and why we're trying to encourage teams to stay away from excavating into the buffer. Next, Ollie. So I'm going to turn it over to my colleague, Dr. Munchie. He's going to tell us a little bit about CLSM and take it away, Javid. Thanks.
Thank you, Pete. So this was obviously something very interesting that Pete passed on to me. I'm here more to learn, not to teach. And part of that presentation, I will to some extent explain what CLSM is. We use it, and how it's specified. Next slide. So CLSM is actually, as Pete indicated, it's a low-strength, cheap concrete material. It's a combination of cement, typically lots of fly ash, sand, water, and admixtures. And admixtures could be mostly air, and the target is about 15 to 30% air. So it's a very fluffy type of low-strength material that is quite flowable. The two documents that actually address this in the construction industry is ACI 229R, as Pete indicated. He's probably already forwarded that to you, and AASHTO, because in the highway projects, this material is used quite a bit. So AASHTO has a lot of specifications, the requirements for producing this material on a consistent quality basis. Next slide. So the key attribute, I mean, one of the key attributes of CLSM is its flow. So it's a simple cone cylinder flow or inverted cone test. You place the CLSM into the cone and you pick it up, and the spread has to be between 6 or 8 inches. If it is less, it's obviously not that flowable. If it is more, it's probably going to segregate a little bit more and maybe not be sufficiently consistent in the sense that it can get you that consistency after it hardens. Next slide. So some comparisons, so you get an understanding of what CLSM stands in terms of its properties, particularly the compressive strength, density, and how it levels out. If you compare CLSM to compacted earth fill, as Pete indicated, so CLSM 28 compressive strength is about less than 2.5, 2.1 megapascal, less than 300 PSI, generally speaking. And that's what we use in the construction industry. If it is more, it becomes a problem, particularly if it's to be excavated, even with the mechanical equipment. So, and compare that to compacted backfill, which is 0.3, much smaller. And that's part of the reason in the construction industry, compacted backfill is being replaced by contractors with the CLSM, because there's no compaction involved. You just place it, you just have to wait enough time for it to set, and you can start the next step of the construction process. Density, 1840 to 2320 kilograms per meter square versus 16, so density is somewhat similar. Placement, it's a self-leveling material. You don't need an equipment, while as compaction for soil is to be done in layers and watched for right amount of compaction to get the right properties for that fill. Next slide. One of the important characteristics of this material is the setting time. Initial set for it to go from a fluid state to a hardened state is about 24 hours or less. But if you're really looking to put some load on it at some point, then we probably have to wait at least for 2 to 3 weeks, because it does take a longer time to set because the amount of water it has in it. Next slide. Excavability. So this is obviously very important for this group. In the industry standards, the CLSM is actually divided into 2 different categories. One is that's excavatable, and the unconfined compressive strength has got to be less than 150 PSI. And if it's more than 150, it is called non-excavatable, but it doesn't mean it's not excavatable. You have to use mechanical equipment to excavate it. The problem, the biggest problem with the CLSM is its strength gain. And that's why it's sometimes harder to get the right CLSM, because if you don't have the right ingredients in it and you haven't really tested it over a longer period of time, it may gain strength on you and become a problem. And it has happened many, many times. So to me, it's easier to specify the minimum strength and achieve more, but it's much harder to specify a maximum strength in concrete or CLSM and then keep it within that, because the properties of concrete are such that the hydration process continues over time, and the concrete or CLSM continues to gain strength. So it's very important to have that upper limit tested and make sure that, as Pete indicated, it doesn't continue to gain strength with time, because that makes obviously it'll be kicked out of the specifications that you're trying to target. Next slide. I know for this challenge, we have focused on the strength, unconfined compressive strength, but there are other ways to people actually specify in the industry CLSM. It depends on what the application is. For example, for highway structures, sometimes they specify the California bearing ratio, CBR, which is some test to verify the penetration of this material compared to crushed rock, for example. And sometimes it's specified based on unit weight or a combination of unit weight and strength, and penetration resistance as I indicated separately as per ASTM C403. So I guess for this challenge, we're really focusing on the unconfined strength, but I think the density is probably something that will play along with that parameter, in my opinion, as well. Thank you. Go ahead, next slide, please. In terms of quality control, there are tests, as Pete indicated. These are the industry standard tests to meet to do the sampling of the material, which is D5971. Compressive strength is ASTM D4832, unit weight, flowability, air content, permeability. So all sorts of tests available in the ASTM standard to make sure that you do meet the requirements to basically satisfy the quality of the CLSM that you're looking to produce. Next slide. So this is the last slide for me, and the question is that where do you get it from? Would you actually make it yourself? I would say it's probably a good idea to go to a ready-mix supplier, because there is a lot of experience they produce it on a routine basis for projects, and their batching system is certified by NRMCA. There's quality protocols they have to follow. So as long as they get the right specification for the material and it gets tested through that process, I think that's probably the best way to get it. I think that's the end of my presentation here. Pete, anybody, if there are any questions, I do have to leave in a few minutes, but appreciate, Pete, if you can take them on if I'm not around.
Great, thank you, Dr. Munshi. So we have a few questions. I'll also give all the attendees some time to enter some more questions, and then we will start addressing them. We will just get started. There's kind of 3 questions in one. The first question, which we will be answering live, is it possible to increase the page limit of the system architecture to 30? At this time, I would say no, it is not possible. We can try to connect with the full Break the Ice team to discuss if this is a possibility, but at this time, I would say this is not possible. The second question, and there's a few questions similar to this, is level 1 drill limit 80 centimeters correct? Please confirm. Kurt, do you want to on this one?
Hey, Ollie, did we lose Pete? I don't see him in the list
Yes,
anymore.
It looks like Pete might have dropped.
Okay, I know he was having internet connection issues earlier, so he may be trying to come back in. He also has the phone number, so he may be trying to dial in if he's lost.
Yeah, I'll be on the lookout to add him back as a panelist.
The rules clearly state that the maximum depth of the CLSM Icy Regolith simulant, not including the border, is 80 centimeters. So you are correct.
Great. And then the next question, the coordinates are not provided for phase 2 for the moon service. Can we use the coordinates from phase 1 for the exploration mission area?
Yeah, and I apologize if that wasn't clear. The phase 2 rules do talk about the mission scenario, and that in this challenge, teams are going to be using a hypothetical lunar ISRU mission, which is detailed in phase 1, and then we put a link to the phase 1 rules. So the answer is yes, you will you can use those coordinates from phase 1.
Yep. Okay, the next question is, please explain the liability insurance requirement, the amount 250,000. Is it per team member or for the entire team? This is a liability insurance requirement for the entire team, not for the individual. Pete, Kurt, anything else to add to that question?
Hope you're good, Ollie.
Okay, and then we have another question. Is 80 centimeters the maximum required drill depth for Icy Regolith extraction? Yes.
You can make your drill as long as you want, as long as it doesn't go down below 80 centimeters, right?
Correct. Is this the background information that is given in the phase 2 competition manual? I think this is a question referring to the CLSM information at large. I don't think all of that information is in the phase 2 rules and requirements document. So again, we're going to be sending all of this information as a PDF. You'll be able to download this PDF from our website. This webinar is recorded and will also be uploaded as a YouTube video, and will also be on the Break the Ice Lunar Challenge website. But I don't think that all of this background information is in the phase 2 competition manual, or as we call it, the phase 2 rules and requirements document.
Correct. This webinar and the content in it is in addition to the rules.
Yep. But you will be getting access to all of this information after this webinar.
Yeah, it'll all be on the website.
Okay, for the level 1 introduction video, when discussing the phase 2 plans, can the video contain NASA public domain videos and images? I think it can. I mean, these are public domain. Anything in the public domain is in the public domain and can be leveraged. Kurt, Pete, call me out if I'm incorrect with that.
Yep. Anything that NASA publishes is free for use by the public.
Yep. Absolutely.
Any public domain, not just
Right.
the public
Right. Not just
domain.
NASA. Very good point. Yeah. Public domain is public domain. So go nuts.
Yep. Can you provide more information on the power supply voltage amps for phase 2, as well as the delineation between the NASA provided power plant and our interface that is included in the total system mass? Let's just recap.
That's probably
that
too
off.
complex. That might be too complex to answer on the fly.
Mm-hmm.
I agree,
There's a
Kurt.
lot
Maybe
there.
they could write that down and send it in. If there's some
Yeah,
misconceptions.
I would send that one in. That might take a panel.
There is no NASA supplied power source as part of this challenge. So please write that one down and send it in.
Yeah, I think that might be referring to some of the kind of structure of the phase 1, where I believe there was kind of an assumption that there would be some NASA provided power plant, but I don't think that's applicable to phase 2. But again, because we're not directly answering this, please follow up and we will basically add this question and the other question to the FAQ page in written format after this webinar. Okay, here's a good question. I was wondering if there's a place to get the ACI 229-R document. Where can they find that document?
Okay, so that's available at the ACI website. So just concrete.org will get you there, and you can go to publications. It's there's a nominal fee for it, $20 to $40, I think. But actually, I think in the rules we might provide a link on where you can find it.
We provided a link to concrete.org, Pete.
Right. So go
So
to
it's right there.
concrete.org, look under publications, and type in 229R.
Great. Okay, so any suggestions on where to get the required insurance? I've talked to several insurance agents and none could set up such insurance for a team. I don't think we can answer that directly right now, but I do think as our kind of challenge team, we have seen challenges with getting this level of liability insurance. So I think that we will need to provide a little more information and guidance after this webinar. But I certainly don't think we have any concrete answers to your question right now, but certainly do recognize that this is one of the issues that some teams are facing.
But Ollie, if some teams are facing it and a lot of teams are not facing it, then it's possible that the teams could communicate with the other teams and, you know, maybe help each other out. So this might be one thing that the forum on our website might be you know, really useful for teams to communicate with each other about certain things where maybe some of them are having trouble and some of them aren't. They can give each other advice.
Yes, absolutely. So we do have a forum. You must be logged into the challenge website to access that forum. But what we can do is basically go out and ask those teams who have successfully procured this insurance and try and get some information from them, and then also try and create a conversation on our forum to kind of open source the knowledge on the right way to get that level of insurance. So again, this will be a follow-up post webinar. We have a question. What is the maximum allowed power usage for phase 2? It was 10 gigawatts for phase 1 kilowatts.
Phase 2 does not limit power.
Thank you, Kurt.
Isn't that right, Pete? Tell me if I'm forgetting something important.
That is right. I don't think we have any limit on power, but I believe it does.
Part of the scoring criteria, obviously.
Scoring criteria.
Yep, it's obviously part of the scoring criteria. So you don't want to use infinite power. Your score will be infinitely low.
Right. Okay, we have another question. Is liability in life insurance the same? No, life insurance is something separate than liability insurance. Okay, there's a question about the number of phase 2 level 1 awardees. Is there a limit to the number of teams that can win a portion of the level 1 prize? Will the number of winners be capped? This is a hard question. We don't have a concrete answer for, I believe. Pete, Kurt?
So the rules state all teams that submit compliant deliverables by the deadline are eligible to win prizes. Will be awarded an equal share of the pile of money. And so if a small number of teams submit compliant deliverables by the deadline and they're eligible, then those small number of teams will get a larger percentage of that pile of money. if a large number of teams are all eligible and they all meet the deadline, that's gonna cut that pile of money into smaller chunks to be spread to those teams. I didn't explain it very well, but it's there in the rules. Go read the rules again. We're not capping the number of teams.
No, we don't cap the number of teams. We cap the prize value. So if only 2 teams enter, basically you don't split the whole bundle. I think there's a maximum value on it, Kurt, if I'm not mistaken.
Yeah, we did cap. Yeah, so that one team, so that one team wouldn't get too much of that money. Yeah.
Okay, questions are starting to slow down. Again, a question about power. Do we need to generate power on our own, or will the power be provided?
Well, phase 2, level 1. Let's just make sure we're all on the same page. Phase 2 has 3 levels. Level 1 is paper design. Level 2 is you test your equipment at your site. And level 3 is you bring your equipment to a NASA site. So, so in that second level where you're testing your equipment at your site, we can't provide you power. You will be in charge of your own power. And then the regulations and requirements and limitations and everything for level 3 is going to be coming out later, after we have had a chance to see what the field looks like, and we've had a chance to go back and look at what we are able to provide and what we are not able to provide. So if you're asking about level 3, TBD. If you're asking about level 2, you're in charge. It's your facility. You figure out how to get your robot, batteries charged or whatever your architecture requires. Hope that answers it.
Great, thank you. So that looks like we have addressed all of the questions. We are just about at time, so I'll give the attendees 1 more minute to enter any additional questions. As next steps, we will be uploading the slides and the video to the Break the Ice Lunar Challenge website. We'll also send an email to all of the phase 2 registrants with the details about this webinar so that you can access it and get this information at a later time as well. I do also want to remind everyone that you must register your team by September 30th, 2022. And again, this is the process of submitting your signed documentation. All the documentation is found on the website. And then that's basically the first component is to register your team. And then you must submit your level 1 concept via the submission form a few days after that. Let's see, what is the exact date for the level 1 submission deadline is November 4th. So you must register by September 30th and you must submit by November 4th. And this is a rolling kind of submission. So getting your team registered and submitting right now is completely fine and recommended, just so that you can understand if you are able to advance to level 2. So we have 1 or 2 more questions. Is there a location where the items that are included/excluded from the mass budget are listed? For example, the equipment that weighs the mined CLSM, a fence around the excavation area.
Pete, do you want to take that one?
Any equipment that's part of your architecture, that is what excavates and delivers, and any equipment required to maintain that robotic system, keep it operating. That's what you weigh. That's the mass you're scored against. So obviously, you're going to have a set of scales or, you know, a mortar pan or something that you're going to dump the material into and weigh how much. That does not count because that's not something you would take to the moon. Okay, that's another way to look at it. Is it the mass of what you would take to the moon to operate your architecture? That's the mass we're interested in. Anything that's
Operate
related
and maintain and fix and repair.
Right.
Yeah.
I hope that provides you some guidance.
Okay, we have just about time for one or two more questions. Can we change team members from level 1 and level 2 if required? I believe that this is totally fine. All that we would ask you to do is to resubmit your the documents that describe your team members, so that we have the most up-to-date snapshot of your team. I do not think there's anything in the rules that preclude team members from kind of getting added or leaving in the middle of level 1 or level 2. Correct me if I'm wrong, Kurt.
I think you're
That
right,
sounds
Alan. Yep.
Yeah, that sounds
have
correct.
to-
I'm pretty
just
sure
have
we've
to
answered this before.
inform the challenge administrators. That's all.
Yeah, just let us know. And this is quite common for team members to kind of shift around. This is a long challenge, right? So, you know, we totally understand that some folks might be working on your team now and might not later, or vice versa. Okay, this is going to be our final question for today. For the registration for the second phase, we need to submit a media acknowledgement form. What does this document exactly mean? Well, I would say basically the document pretty much lays out what you are acknowledging. It basically gives NASA the rights to promote your team via social media. So you know you should just read that carefully, and in essence it's enabling NASA to share information, top line information about your team and your submission.
Right. Without sharing your intellectual property.
Yeah, this would be things like celebrating if a person won. We'd be able to basically just share your team name and the submission name. This is in no way, shape, or form actually sharing any of the kind of intellectual property or details about your submission. All right, and with that, we are concluding today's webinar. Thank you very much to both our panelists and our attendees. Some super interesting discussion. And again, just to remind you, please complete your required paperwork and submit to the challenge administrator via email and via the form by September 30th. And we are super excited to see all of the innovative solutions that are proposed. And with that, we will be concluding today's webinar. Thank you very much.